And Scott is going to pace now and speak about storage.
In that order. Free NAS. This year we're announcing the official sponsorship of OpenFiler.
Make sure you cut that from the video.
Yeah, cut that from the video. We're actually starting now, yeah. Okay, hey, I'm Scott Allen Miller with the NTG Labs. I'm a technical fellow, and today we are covering Storage 101. So as Rob mentioned earlier, this crowd's pretty technical, and you guys know how to install stuff. So I'm going to be covering a lot of things that you guys already know, but I'm hoping a couple things. One, to kind of put things in some new perspectives that might be useful to you, and more importantly, well, I mean, trying to help you is important, but the bigger thing here is really I want to establish kind of a baseline of storage knowledge that we can use to build on because this is being recorded and this is going to be available to people who are looking for MangoCon resources ahead of coming to, say, next year's conference or our meetup next month. We want to have kind of this foundational knowledge in storage that we can point them to so that we can, in the future, continue to build on it. Storage is a major topic. Constantly new things happening. This morning's topic on fog computing and fog storage and those kind of things show this is a big topic that we really care about, we get excited about, it affects us a lot. Storage is a major component of a lot of IT work and certainly of every business, right? Everybody has storage of some sort. Businesses have data. So, getting started. At the very base level, and so this is going to be a technical talk, this is not like some weird theory of storage. At the very base level of all storage, we deal with what we call block devices. But I mean this physically, physical block devices. And we all know what these are, right? This is traditional spinning hard disks. This is SSDs. This could be memory, like RAM sticks, just behaving like disks, whatever. We always have this physical at the bottom layer. And the reason that I bring this up is because as we get talking, people sometimes start to be like, well, wait, are you saying that there's no disks or anything at some layer? Because we get so many levels of abstraction. We get so much complexity or just stuff built on top of disks that sometimes we forget that there's always going to be a disk at the bottom, right? Now, someday we're going to come up with some cool new storage that does not involve disks, and that will be a cool new future, and we will discuss it when it comes. But for now, disks of some sort rule the world, right? Well, they at least store the world. So the thing that makes these things storage devices, right, this is where it starts becoming, we don't normally think about it. Right? Well, we all know what a disk is. Plug it in, store stuff on it, right? But what makes it a storage device is that it actually implements one of a series of very similar interfaces. The common ones include the SCSI command set. Everyone knows SCSI, right? SCSI. It's been around for forever. It's incredibly useful. It's very basic. It's actually a networking protocol for those who've never really stopped and thought about it. I'm sure all of you are technical. All of you, if you took the time, would be like, oh, it must be a networking protocol. But if you've not sat down and really thought about it, you may not realize that it's actually an L2 protocol, kind of like Ethernet, right? A little bit different. It's got some features that Ethernet doesn't. If we want to be really, really technical, SCSI is actually a single block that represents L2 through L7 of the ISO OSI model, right? It actually is 6 layers in one. Only layer 1 is not included, and layer 1 is defined by other components of SCSI. So if you really want to get deep into it, things like Ultra 80 SCSI or Ultra SCSI 80, right, defines even the L1. But SCSI itself, just the SCSI command set, is L2 through L7. If you're not a networking person, that's not information you need to know. Just kind of building a foundation, right? If you're coming from a networking background, that stuff is incredibly interesting. So SCSI is an important command set and is kind of the grandfather of all modern storage interfaces. But some others came along. ATA for primarily desktops and laptops. They were kind of like, we just don't need everything that SCSI can do, because SCSI's got some cool features like you can share disks, which we're not going to talk about. ATA kind of made it lighter, and it made it easier for drive manufacturers to make something cheaper. But if you're implementing the ATA command set, which again is an L2 through L7 stack component on the networking side, you basically look like SCSI. Few different commands, fewer features, they behave the same. After SCSI, they said, well, we kind of like to get a little bit more modern, and they implemented a thing called Fibre Channel, which has nothing to do with fiber. It can be implemented over copper. And that's why it's spelled F-I-B-R-E, not because it's British, but because it's not actually fiber. It just sounds cool. Fibre Channel essentially is a new version of the SCSI command set. Slightly different, does basically the same thing. These three protocols represent effectively all storage. Not 100%, but effectively. You can go out and make your own storage system if you wanted, but we all know how storage works, and the expectations are that anything you create will behave very close to these systems, or if it doesn't, it will simply lack a bunch of functionality unless you've come up with something really cool and can add it in. But chances are, if you could, the SCSI people would have done it, because that's what they do all the time for decades. In modern usage, these technologies move forward, right? SCSI is actually only the protocol. What has happened over the years is that people came up with newer and faster versions, and we used to have what we called parallel SCSI, but it had nothing to do with the command set. The L2 through L7, still exactly the same. It was the L1, the cabling, the electrical, the voltage, the speed of processing. Those things were the things that were changing. In the early 2000s, they proposed that the old parallel cables, the ribbon cables that we used for SCSI, or the big rounded, which were really just ribbons rolled in a circle. But they had cool rubber bands on them, held well together, it worked really well. So they proposed, well, parallel just doesn't scale. We're getting faster and faster. We need to move to serial. So they did. So they implemented SAS. It's the coolest thing ever. It's just SCSI over serial. Right? It is great. It helps airflow in your case. It gives you nice little connectors that are way easier than the old ones. It's cheaper to buy stuff. It's just better. But the reality is it's still the same L2 through L7 SCSI command set that it always was, and just a new L1 with better cabling, faster signaling, and we even have the same things that we used to. We used to have, Ultra SCSI 80, Ultra SCSI 160, Ultra SCSI 320. It just kept getting faster and faster. We went to SAS, and then we're like, we're going to have SAS 3 gigabits per second, SAS 6 gigabits per second, SAS 12 gigabits per second. We changed how we named it a little bit, only barely. Everything's continuing just like it always did. We just stopped saying SCSI every day when we say SAS instead. Same difference, same SCSI command set. Same thing happened with the ATA protocol. Their ribbon cables were even worse. They were shorter, they blocked all kinds of air, and they couldn't get them to go fast. And so when they made the jump to SAS, they said the same thing with ATA. Boy, these would be way easier if we moved to serial. Then we can make it faster, and we can make connectors that are shared with SAS to make manufacturing cheaper. And so they did. They took the exact same protocol, pumped it over a serial connection on the L1, kept everything else the same, and kept making it faster in the same way. And that's why we have SATA today, or SATA, depending on how you want to pronounce it. If anyone knows of a standard on that pronunciation, let me know, because I've never figured it out. But I like to say SATA, but I'm pretty sure most people say SATA, so I try to say it, but I get it wrong all the time. Fibre Channel, likewise, continues to develop. Same command set, very little has changed. And I should say, SCSI, for example, has moved on from SCSI 1 to SCSI 2 to SCSI 3. The protocol has updated in very small ways over a long period of time, but it's almost completely under the hood, and you never think about it. But it is there. It's not 100% static. Just like TCP/IP does update a little bit every so often, and I don't mean the jump from 4 to 6. That's dramatic. SCSI updated in very minor ways. Storage has not changed much. Fibre Channel gets faster and faster over the years. I believe that we currently have 32 gigabit per second Fibre Channel coming down the pike. Should be available in the market very soon, but people are working with 16 gigabit right now, which, as we know, is a good, 25% faster than the fastest SAS right now. But not too many people implement Fibre Channel direct to disk anymore. You can still get it, but typically we use it at another layer, which is interesting, and we're going to get to that in a second. But you certainly can buy Fibre Channel disks, right? In the SMB space, a lot of people are actually surprised to find that in the enterprise space, at least for a very long time, nearly every disk was Fibre Channel, not SAS or SATA, right? Which is interesting because when you start thinking about what we're going to get to using the interface system, it starts to explain a commonality in understanding how storage works, which makes things easier. Okay, so the things that make these similar is all three of these protocols, and any other you're going to discover that are like them, present a disk, a logical disk, to whatever system is going to talk to them. And a logical disk is really just a block device that you can write to and read from. Right, it's a very basic thing. And SCSI does a few other things, right? It can do like reservations. It can tell the system that it's going to write to that and not to mess with it quite yet. But it's all, details under the hood. We really don't care about that too much until we're like building our own SCSI system. It's just important to know that it has a lot of cool technology. It has some, quiescence stuff. It's got some sequential ordering logic that you can implement that helps performance sometimes. So that stuff's really interesting if you're really into storage. But if you just want to understand basically how they work, they read and they write. The disk takes care of actually putting it on the disk. It takes care of actually pulling it off the disk. And with SCSI or with SAS or with what we're doing is we're just specifying where on the disk we want to grab something or where we want to put it. It's very basic. And so what we get with all these things is a logical disk. And by logical, we mean the system, any system that connects to the other side of a SCSI connection, or the other side of a Fibre Channel connection, sees a disk object as the interface. Does that make sense? If people have questions, grab me as I go, because I don't want to skip over an important definition and have somebody be like, I don't get the logical disk thing or something. So the controller sees the disks and then presents it onto the next layer and says, here's a logical disk that you can work with. And it is presented as a SCSI device or a SATA device or a Fibre Channel device. And they all behave exactly the same or so close that we just don't care. So we just call it a disk, even though technically it's a SCSI disk. This idea that what you're getting is a logical disk becomes one of the most important things that we will ever learn about storage, other than you should always back it up if it's important. This idea that you get a logical disk as an interface allows us to look at disks as building blocks of storage. And this is where a lot of people kind of immediately become lost, I guess, when they go to look at storage, because it's just not common to look into how this works under the hood. And it's worth taking the time to really, really think about a logical disk interface, because it's an incredibly powerful concept and it colors everything. So if we then want to do something with our disks, we can attach to them directly. And we're going to talk about this first, and we're going to come back to what we can put in between. Under normal circumstances, what we want to do, and we're going to put stuff on a disk, right? We all know it's going to be data, but we're not going to get to that yet. You want to put something on the disks. And so we come up with this concept of a file system. And what a file system is, right, is basically a data structure. It's technically a database, which is really interesting to database people, right? So I kind of fall into a bunch of different lines. I get really excited about the ideas of file systems because it's just cool. And, the EtherStore guys are here and they get into file systems. Like, it's fun stuff, right? You get excited about file systems. He's like, no, we really don't. But it's cool because it's actually data structures. And you can do all kinds of different things with file systems. But at the end of the day, there's actually something kind of neat that happens. And that is that file systems all get to look at logical disks and see them as essentially all identical. Then you apply this data layer. And the data layer is actually a translation system, right? And what it does is it translates from a standard of what we often say block device, but a logical disk, or a disk appearance. I like to use that term. It appears as a disk. It takes a disk appearance, applies this data logic, and in the file system driver, it converts that into what we see as a file system. And file systems essentially always look the same to us. And it's not quite true. They're not always identical, but they're really, really similar. And what we'll say Windows does is Windows has a virtual file system that it layers on top of the actual file system so that they can present a uniform file system to us as the end user. And that thing will sometimes pull out features, right? If you're using NTFS all the time and then you switch to FAT32, everybody remember FAT32? It was super cool. We were like, cool, FAT32. So when it presents FAT32, their uniform file system appearance interface will remove things like the ACLs from view because it knows that it doesn't implement it under the hood, and it would be very confusing if it let you try to implement them and then they didn't work. So it does a few things to like not make it 100% uniform, but it presents a very standard interface that makes it easy for us to work with no matter where we are in the operating system. It's always going to look basically the same. Exact same thing happens on Linux. It's called the virtual file system, VFS, which is a little bit confusing because it sounds like something else, but the VFS takes any file system that you put onto it on Linux and presents it to us in a standard uniform way so that we, as the end users, and really meaning the operating system, can always look at any file system that we have and treat it equally. It doesn't have to know what's going on under the hood. We don't need to know if it's XFS or NTFS or ext3 or ext4 or ButterFS or CFS. So many options, and file systems are cool if you get into them. It's a lot of fun to learn about. But we get a standard interface. So we call this a file system interface or a file-based interface. We now have two standard interfaces that we interact with in pretty much all cases. Block, or disk appearance, and file. We're used to dealing with file the most, because as end users, we start using it, right? That's where we start being like, I'm just gonna make a folder directly on the file system. Sure, there's a graphical interface, but we know we're interacting with the file system. Like we understand that. Even like non-technical users pretty much understand it at this point. The file interface is kind of a end user exposure, or it can be exposed to end users at the very least. And making files directly on it makes sense and things like that. We are then able to take that interface, because it's a standard interface. This is one of the cool things about standard interfaces, is that you can encapsulate them and throw them somewhere else. So someone came along a long time ago and said, well, this file system, this virtual file system abstraction is so powerful, any system that wants to look at any file system simply implements this virtual file system interface, translates what it gets, and presents this standard thing. Well, we can just pump that over a network, of course. All we need is a driver that connects this side to that side, and this side has to expose the same virtual file system interface. So cool. So they did. And that's how we got protocols like SMB, CIFS in the old days, NFS, Andrew's file system from IBM, AFP from Apple, and countless others. I mean, dozens at least that have, more or less risen up, gotten known, but about 3 remain of any serious use, and SMB and NFS pretty much rule the world as far as these. But what's interesting is we don't really care which of these we use under the hood. We talk about it because we're IT professionals, right? So we're interested. Again, another cool topic. We can talk about the networking performance differences and feature differences between SMB and NFS. We get into this stuff, right? But for end users, or for just anybody who's not in that particular decision-making process, what they care about is that after their network driver, which would be an SMB client or an NFS client under the hood in your operating system, you never really look at it, is taking that network connection and changing it into a standard file interface. So this is what we call mounting a drive, right? And if it's a physical file system sitting on your system, we mount it. If it's a network one coming from somewhere else, we mount it in the exact same way. And the end user, whether that's a database or an actual end user or an IT professional, we all, in the end, see it as a file system exactly the same as every other file system, and we can use it exactly the same. It might be slower, it might be bigger, but it works exactly the same. We don't have to learn how to use a map drive, right? It doesn't matter if it's Windows or Linux or anything. They're all the same. So this is a really powerful concept, and this is how they came to this conclusion. It was through the use of standard interfaces. So on the file side, it's pretty cool, and we use it all the time. Map drives, woo! So that's pretty easy to understand because we look at it all the time. So let's go back. let's look at block again. We had this standard interface. Well, on the file side, they simply said, well, we could encapsulate it and do some interesting things with it. Now we have this powerful concept of a standard interface. We must be able to do this on block too, right? Because standard interfaces are standard interfaces. Anytime you have one, you can do something cool with it. Okay, so in reality, this is not the order of events. They did this with block long before they did it with file. So one of the first things they did with block is they said, well, we want to layer some services on top of our disks. Disks are really kind of fragile and expensive and inflexible, and they're physical, right? Who wants to deal with physical disks when you don't have to? So one of the first things they said was, well, we need to make our disks bigger. But we can't just manufacture bigger ones, so how do we solve that? But we need to see a bigger disk, and we need them to be more reliable, and we just whatever, right? They had all these things they wanted to do. And what they said was, well, what if we took a bunch of disks and we came up with a way to aggregate them and present them through a standard interface again? And I'll never get the date right, I feel like it was 1988. They did this at IBM, and they came up with a way to take a whole bunch of, and we like to say disks, but this is wrong. What they're doing is taking a bunch of disk appearances, because all they're doing is accepting a standard interface that looks like a disk, and then doing some magic, which we can talk about some other time, and presenting it again as a disk. And we call this RAID. Right, a redundant array of inexpensive disks. I refuse to use the new backronym that they created to make it sound cooler than it actually is, and which is a redundant array of independent disks. Yes, we don't buy that crap. It was a reference, the original was a reference to using Winchester disks, the traditional spinning disks that we use today. There were much more reliable, much larger, much more expensive disks at the time, and there still are, just no one uses them, that they did not intend this system for. The system was intended to take commodity disks and make them functional like the really, really expensive enterprise ones. Everybody seen that in any other area of IT, right? We see that in things like AMD 64 commodity clusters being used to replace mainframe workloads is a very common one. Things that 20 years ago we would only look at mainframes or mini computers. Things like PA RISC and DEC alphas and things like that. Those are the only things we could use for certain workloads because they were super reliable and super fast and it had all kinds of enterprise reliability. But today, we can really just take, VMware or Zen server, add some storage magic to it, and suddenly we've got really, really awesome commodity clusters that do some really interesting things and make, in many, many, many cases, mainframes and PA RISC machines and such, and make them go away. Right, and of course, EtherStore does a similar thing by commoditizing just the storage layer, and Scale takes the storage and the compute and does the same kind of thing. So we have lots of vendors here who do those exact things, right? Replacing mainframes or replacing expensive disks, whatever. So if we look at how RAID works, it's really just accepting a standard interface and then giving out the same standard interface. And so because of this, any system that looks at RAID sees a disk, which most of you know, right? We're all used to dealing with this. It sees a disk. And as far as any system is concerned, it is a disk. No system above the RAID on the stack sees it as RAID. It does not understand that it's RAID. It understands it's a disk, because a disk appearance is identical no matter what's under the hood. That's the magic of standard interfaces. Well, pretty soon, people said, RAID is really cool, very, very handy. I love what we're doing with this, but we need a little bit more flexibility. RAID is great for giving us speed and reliability, or was. It's starting to age now. Now we're looking at technologies like RAIN to kind of overcome some of the limitations. But for a really long time, RAID was like the only game in town. Right? It was the only way to do this. And so what they did is they said, well, we need another layer, a layer that's going to take the RAID, or anything, it doesn't have to be RAID, it's always a disk appearance, and make it more flexible. And someone invented a pure abstraction layer. And I don't know when this came about. And this abstraction layer is not one that takes lots of disks and turns it into one. It's not a system it's just an abstraction layer that allows you to take whatever is shown to it and present it in any way you want and do nothing else. There's no magic to it. And we call this because we started thinking of disk appearances as volumes, because some people were starting to get confused by everybody saying disk a lot. So to make it easier, we called it volumes. Now we have disks and volumes that are the same thing. I don't think it made it easier. And in the RAID situation, we call them arrays. I don't know why we keep renaming the same interface. So we have disks that became arrays, and now they're going to become volumes. They're all logical disks. So the logical volume manager, as we called it, and it became abbreviated quickly to LVM, is a layer that accepts a standard disk interface and allows us to do things like what we think of, for example, as partitioning, right? We're all used to partitioning, which is actually something we'll cover again in a second. But logical volume managers allow us to divvy up the space that it accepts as a standard disk and present it as more standard disk interfaces. So any system that's looking at an LVM will see one or more disks. The LVM knows what's coming in and how it's presenting what's going out, but no system looking at it sees anything other than more disks. It might see one, it might see 100. You could have a single RAID array built out of a single disk behind it that hits an LVM, and the LVM could present 1,000 probably really small continuing disks onto the next layer. Now, what's really cool is that LVMs are often put onto RAID controllers. And you'll see this, I think Smart Array does this a bit, that you can create volumes directly in the Smart Array controller. PERCs do not. So if anyone's working with Dell and PERCs, there's no LVM layer on a PERC controller or an LSI controller. But if you're working with an Adaptec or Smart Array controller, very commonly you're going to have this feature. It's not a big deal because you can implement this at other layers, but it is kind of handy sometimes to have it in hardware. So you have this LVM that sits on the RAID controller itself and allows you to present on all these different volumes, which is great because let's just say that you're running something like VMware, and it is not going to be happy if it only gets one disk. It requires two, just how it works, right? Well, if you control the LVM layer in hardware, you give it 2 disks. It doesn't know what you have underneath. It has no way to find out. It is not within its purview to see through any abstraction layer because it sees 2 disks. That's all it knows. It doesn't know where they come from. It doesn't know why. They are presented as SCSI objects. The power of standard interfaces and abstraction. Wonderful things. Now, the same logic was rapidly applied in the operating system. People said, well, you know what? If we can have LVM close to the disks, we could have it in the operating system. I don't actually know the order of events here. Again, it may have been in the operating system first, it's pretty likely. So in the operating system, we say, well, people only gave us 1 disk. This is separation of duty problems, right? So the storage team, or the guy who built the server, doesn't matter, gave me 1 disk, but I need 5 as the systems administrator. How do I do that? Well, we have this tool called an LVM. It works great in one piece of hardware, it'll work great in this piece of hardware, well, in the software. And so in the operating system, we typically, and just before people are like, well, I wish I had one of those, all enterprise operating systems have an LVM layer. It's not always called LVM, right? In Windows, it's called dynamic disks. In Linux, it's actually called LVM. They just not original. IBM calls it LVM. Solaris calls it something, some kind of stellar name or something. And then they're all over the place, right? But everybody has one because they're super important. So we have this LVM now in the operating system. So we don't care what we're getting. We can take the disks that are presented to us, add LVM in our next layer, and we can totally manipulate it however we want. Want 5 disks from your one? We can create 5. I don't have to ask anybody. I don't have to tell them how I'm using it. And also important, the storage guy can't look and see what I did. Because to him, he's sharing me a disk. It's all just data on the disk to him. To me, I'm getting 5 disks. Ha ha, the magic of LVM. The power here is actually bigger than you might imagine. Because he might present me 1 disk and I need 5. But he might also, and a real world thing, he might present me 30 and I need 1. Actual thing. right? And we can, you can grab me to talk about the weirdness of why these things happen, but it might be a real thing. So basically, we've completely abstracted. We can take any number of incoming disk appearances and have any number resulting outcome. And not only can we, now this depends on the LVM implementation, but one of the standard features that everybody's super excited about is if the system's running and we need to add more disks to it, we can, because of LVM keeping all the separate pieces from interacting with each other and abstracting it away into the magic between two standard interfaces, it's able to allow us to grow the size of connected disks. It allows us to grow or shrink the size of resulting disks. It allows us to add new disks on either side, remove disks on either side, do all kinds of really cool magic because it has full control and knowledge of everything that's attached on both sides and abstracts it completely away so that every other piece doesn't know what's going on. They just see disks. Then somebody said, you know what, we have all this control high up in the operating system. Wouldn't it be awesome if we could take a new crazy idea called snapshots? LVMs are where snapshots are implemented, because LVMs are cool. Because LVMs are the perfect place for it. LVMs are only there to manage your storage. They don't exist for some other purpose. RAID is there to make it big or fast or reliable. Right? One or two or three of those factors. That's what the RAID does. It has a job to do. You don't want to put these things on top of RAID because it's busy, right? Don't encumber it with that. And the file system is doing its own thing. It has a specific purpose. You don't want to force the file system to have this functionality that it might not need. You don't want you don't want the disks themselves doing it because they don't understand what's needed. The operating system is where the logic exists to know what applications are where, what can be snapshotted, what can't, when it should be snapshotted, when it shouldn't, when performance matters, when we have a moment that we can quiesce. The operating system is where the knowledge is, where the logic is, and so having the operating system able to control the LVM that does these things is the perfect place. It's the only place where snapshots make tons and tons of sense. Now, we'll get to a stack in a few minutes and talk about where you can kind of make it work without the OS. So we then have this LVM creating these disks. Pretty standardly at this point, we're going to take those disks and put a file system on them and convert them to files so that people can use them. But if you're following along, you've probably noticed that every single layer along the way implements a standard interface. Maybe I mentioned this. So there's a standard interface in, a standard interface out. What that means, of course, is that if we wanted to put an LVM before the RAID level, we could. If we wanted to have RAID on LVM on RAID, we could. We can actually have an infinite number of different layers implementing standard in, standard out disk appearance interfaces and build any amount of complexity into this as we want. Now, I wouldn't recommend that. Right, start getting weird. But one of the things is in labs, for example, people will actually do this. Well, I really want to try out RAID 5 and RAID 6 in different scenarios and just test how to build it, right? Well, you don't need to do anything crazy. You can go, no matter what RAID you have underneath, maybe you have none. Maybe it's just a disk, you put LVM on it, you put 5 disk appearances forward to the operating system, and now you want to play with RAID. Put RAID on top of the LVM and make a RAID 5 array. And then blow it away, make a RAID 6 array. You have 5 disks to play with as far as the RAID's concerned. It has no idea that it's not actually 5 disks. So while it's a dumb idea in production, really, really dumb, it is an interesting way to be able to learn how to do things or to test theories or to, in some cases, there are legitimate reasons why you may need to do weird things, right? And one of those is, and we'll get into this, there's some cool stuff that you can do when your vendor has really awkward requirements, right? Sometimes your vendor's like, we demand RAID 5. Really happens. And they also demand spinning disks. And you're like, okay. So how do you deal with this? Well, you can actually give them RAID 5 on disks and do what you think they want you to do. But, one of the nice things is, because it's fully abstracted and your vendor probably can't see everything you're doing, you can build a RAID 10 physical array, present very, very reliable storage forward, put an LVM on top of it, create 5 disks. Yeah, you're going to lose a little bit of overhead, but you're going to get the RAID 10 reliability and still have RAID 5 to show to the vendor. Tricky. So weird cases. These things come up. All right, so I want to back up again, because this is the stack in like the physical world, right? We know what this looks like when we were building a server physically, or a desktop. I mean, it applies to everything. They're all the same. We don't normally do that much on a desktop, but on servers, really, really commonly, like the standard way to build a server in 2002 was disks with RAID, with LVM, possibly on the RAID, definitely LVM on the operating system, then the file system. That was the layers we expected in a normal, standard enterprise OS deployment. Unless you're on Windows, and then we didn't hit that until 2003, right? 2002 you couldn't, 2003 we expected it. And it was a major selling point of everyone else versus Windows up until 2003. A lot of people don't remember this now because we've had the VSS layer and the dynamic disks layer solid with all the features since 2003 in the Windows world. But in 2002, it was a standard thing for every other operating system to mock the Windows world because this feature was so standard and so important, and they didn't implement it. All right, so today we have virtualization, right? Like everywhere. And we know that storage gets a little bit more complex when we're virtualizing. So how does this work? Well, the underlying hardware is normally the same. We're going to have disks, and then we're going to put RAID on top of that, and then we're going to present that to the hypervisor instead of to the operating system, right? And if this will be a virtualization 101 talk. Because this is a storage 101, I don't want to get too technical at the virtualization level. So if someone's watching and doesn't understand where the virtualization is, or if someone in the room has a question, grab me afterwards. We will be making videos for virtualization 101, so I want to keep these separate. So we're going to make some assumptions as to knowledge here. The hypervisor is going to accept those connections from the RAID layer. And then it is going to, and now this gets really cool, it's going to put a file system on top of them. Well, now we're at the file level, right? Well, yes and no. The cool thing that every virtualization product does, but doesn't have to, it's not a rule, it's just what they do, is comes up with a specific way to take a file and present it as a disk image. So we can now convert from block to file, and now we can convert from file to block. So in some cases, it's disk appearance in, disk appearance out, two standard interfaces that are the same, but in others, we have the translation layer, disk image in, file out, or file in, disk image out. This gets really cool. Now we have files that represent disks. Neat. Which is in reality kind of similar to what LVM is doing under the hood. We don't really think about it, but that's basically what LVM was doing, implementing a really light file system without telling you, and making some files without showing you, and not letting you manage them through the virtual file system through the standard interface, but keeping it all abstracted. But that's what's normally happening under the hood. So now that we have files that represent disks, we convert back to block, or into disk images, disk appearances, and we can now do anything we want with these files. This is cool, because now we have a standard file interface so we can play with them in new ways. So the stack is the disks on the bottom, and then the RAID, and then the file system. And then files that act like an LVM layer with features like snapshots and being able to grow and shrink and thin provision and that kind of stuff. And then the operating system inside the VMs receives block storage, disk images from those files, and then it can layer on whatever it wants, standardly an LVM layer, and then create multiple disks, But we can have multiple disks directly from the hypervisor as well. We can have 2 disks or 3 disks, and each one's represented by a file. Very powerful. You can also do some raw things, right, where you actually create LVM volumes and present them directly on, but most people don't, and we don't normally recommend it. And not meaning like it's a bad thing, just it's not a standard use case. So we have these really, really powerful things. We haven't really changed anything going to the hypervisor and to virtualization. We just added this one extra bit of abstraction, which is really cool because we have files that turn back into block, which gives us some pretty powerful analogies. One of the things we can do with that, of course, is we can take those files and copy them and store them on a file system somewhere. Just, drag and drop. It's a file. Your entire storage system is now a file. That's really cool. And we didn't used to be able to do that, but today we take it for granted. But it's a pretty neat thing. Now, there's lots of different ways that these things work in the real world. These are like standard stacks when we're dealing with those standard components like VMware and Zen Server and those things. But as we know from being at places like MangoCon, there's some really cool new stuff going on out there by companies like StarWinds and Scale and EtherStore and lots of others. But we don't mention the others, they're not here. So what is really big, right, the big new thing that's going on is, well, there's a few, but a really big one is RAIN. And RAIN is what all of these vendors are doing to some degree. And what RAIN is a new way of looking at the RAID problem. RAID is cool, right? I mean, we've been using it for decades. We all live and die on RAID. If you're new to IT, you're going to be looking at it all the time. If you've been in IT, you've been using it all the time. It's everywhere. We're so used to it, it's an assumption. It's one of those things we accidentally keep calling a best practice when in reality it's a rule of thumb. RAID is almost always the right thing to use, but rapidly that's changing. And right now we're still in that, well, it's really rapidly moving from 1% of the time we don't to 5% of the time that we don't, but that's accelerating. And in the next 2 years, we're gonna really see probably that 50% mark get passed. And RAID is going to become the niche solution, but an old one, and it's gonna linger on, we need to know it. So RAIN addresses the problems with RAID. And what are the problems, right? People want to know. And this isn't a RAID talk, so we're going to cover a lot of that at some point in the future in a RAID in-depth. We definitely want to do a RAID 101 and a RAID 102. But RAID, for example, has effective limitations of not being able to grow super big without becoming recklessly dangerous and becoming very expensive at very large scales. It just is expensive to put, say, 500 disks in a single box. You can't buy boxes to handle that, right? So you have to, are you gonna custom order it? What are you gonna do? It's gonna cost a lot of money and you need to be a storage engineer to handle it. The approach that people are taking is RAIN, which allows you to take multiple machines instead of multiple disks. Each machine having a disk, or maybe 100 disks, probably not 100, but it could happen. And allowing those to talk to each other over a network, hopefully a fast one, but not necessarily, and share the same kind of data that RAID did, but make it so that you're replicating between the nodes. And it's not, so a lot of people assume that what we're doing is network RAID. And network RAID does exist, and network RAID is really kind of it's a subgenre of RAIN. So we don't want to pigeonhole RAIN. Everyone's implementing RAIN differently, and RAID has a lot of different ways of being implemented itself. But if you took RAID and just used a network connection in the middle of it, we call that network RAID. And it does really simple things, like you can mirror whole systems between each other, and it works. And often with 2 nodes, we do that kind of stuff. Works fine. Can be very reliable. But a lot of RAID doesn't work well with the latency of a network. Rebuilds can get really awkward. So RAIN typically is going to address that in some unique way. And this is where every vendor has their magic sauce, right? And the way that someone like Scale does, because I know Scale's system pretty intimately, is they take very small chunks of data on any given node and replicate it to another node at an independent, very small block layer, right? So instead of mirroring a disk, which is what we did with RAID was all about taking a disk appearance. It didn't know anything that was going on under the hood. When we get to most enterprise RAIN implementations, we're dealing with something that has a lot more logic, right? It's a lot more aware of what's going on under the hood, so it's not implementing like an immediate abstraction. It is looking under, what it's actually doing is putting a file system onto the disks directly, just like we do with the hypervisor, right? This is where we kind of learned this. And taking that and abstracting things out as very, very small chunks and then replicating it in whatever way we want, right? So with scale, it's a block level mirror that goes to 2 places, but you don't know exactly where it's gonna go. If it's someone like EtherStore, they take a little bit larger chunks and put them in lots of different places because they're assuming, in one case, scale is assuming super, super, super enterprise reliable servers. 2 copies is pretty good. EtherStore is assuming ephemeral desktops that may come and go, may not be super reliable disks, might be getting kicked under someone's desk, so they make more copies to deal with durability in a different way. But the same, at a very high basic level, the same kind of things are happening. Replication of small chunks of data, which are then at some point presented on as a disk. And actually, this morning's presentation that Rob did was perfect because we got to see tons and tons of underlying RAIN nodes on EtherStore. And in the end, it was a disk, right? Every system that you wanted to work with to talk to that sees a disk. That's all it cares about. Now, it might be faster, it might be slower, it might be bigger, it might be smaller, but it's still just a disk. 15 minutes. Oh, 15 minutes, okay. That looked like 6 minutes when you do it like this. Okay, 1, 5, 1, 5. Okay. So RAIN is a really, really important new concept, but it's not changing how we really use things. It's just understanding that now we can take the basics that we did with RAID and start using it across multiple machines to kind of make it grow, make it more durable, make it able to get bigger. It's a more modern approach, but not applicable to every workload. So now that we have all these standard interfaces, we have new things that start popping up. What if we built a device whose sole job is to provide disk appearances to other machines? That would be cool, right? So someone came up with this, right? An entire machine that has basically every layer, or might not, doesn't necessarily, but you take a disk and present it over a network. So a disk appearance over a network. Cool, yes. So we call this a SAN. Technically, it's a disk array. The actual connection is called the SAN, but we don't really say that. So SAN stands for Storage Area Network, and technically, it refers to a dedicated network on which block storage or disk appearances are given network access and things consume them. But we're cool, we're in IT, we're gonna be a little bit loose with the terms, and we start to call the devices that do this the SAN. We all do it, so get used to it. Try to, anytime you see SAN, remember it really refers to the network, but the person talking is almost certainly referring to the storage device that's doing it. And I do this too, so great, this is how I say it. And I'm gonna continue to say it in this talk, so deal. So the idea of a SAN, a lot of people heap a lot of things onto SANs, right? Oh, a SAN means it's gonna be super fast. It's gonna be super big. It's gonna be super reliable. SAN does not imply this in any way whatsoever. SAN implies a disk appearance via a network encapsulation. And in some cases, we invented this early. We, not me. Fibre Channel, which we talked about, not fiber, it's F-I-B-R-E, was invented for one of the primary purposes, yes, to be faster, yes, to have a few more features, but primarily to make it that we could do storage area networks really, really easily. It is a SAS-like, a SCSI-like protocol that handles the complexities of SAN naturally, natively. So we don't have to add anything new, right? And technically, we can build SANs out of SAS. I don't know if anybody's tried this. There's actually SAS switches. You can attach a SAS device to multiple things over a SAS network. Nobody does it. It's cool though. It's pretty fast, but it's very limiting and it's always expensive, so people don't really do it. But you could. And that's important. You can also do it with USB. You can also do it with IEEE 1394, and people used to. It was actually a thing, IEEE 1394 SANs. And now Apple's doing it with Thunderbolt. They have several Thunderbolt network SAN devices on the market. They're really silly, I don't recommend them, but it's something that people do. They're still doing this like, it's meant to be local connection, but it's technically a L2 network protocol, so we'll just do it. So Fibre Channel is a basic native SAN technology. Block storage, disk appearances on a network. But then we said, well, SCSI is so standard, we've got SCSI everywhere, and Fibre Channel is only in L2, we're lacking all the cool features of L3. What if we wanted to put SCSI over anywhere so we can route it, sorry for the British. I forget that every time. And so what they said was, well, I mean, SCSI's just SCSI, all you need is a disk appearance on the other end, right? So if we take SCSI protocol and encapsulate it in TCP/IP, we have magic. Our SCSI will go somewhere else. All you need is a driver that can take the TCP/IP connection, rip off the envelope, and you have SCSI again, native, just like it was as if it was directly attached. Nothing can tell other than the driver component, right? And so iSCSI was born. Literally SCSI over TCP/IP. Nothing complicated. Well, it's complicated to use it, right? But it's not complicated in what it is. It's a really, really simple thing. Anything that implements iSCSI, after it has removed the TCP/IP wrapper, it sees a local disk. It has no idea that the disk is not sitting directly attached to it. It doesn't know if there's LVM on it. It doesn't know if there's RAID on it. It doesn't know if it's coming from a SAN. It doesn't know anything. It's a disk. That means we can use it anytime, any place that something's a disk, or if it's Fibre Channel, we can use it like it's a disk. SAN simply means that we are taking a disk appearance and making it available over a network. Now, what people often associate with SANs, and does happen, right? In no way do we say it doesn't happen, it's just that it doesn't mean that. And I do have an article on MangoCon that's, I think, well worth looking at. It's I don't know how to find it, but it's an article about the Netgear SC101. It's the effectively the most basic SAN that was ever made. It is a one disk to one disk appearance. There's no LVM, there's no RAID, there's no nothing. It implements a wacky proprietary SAN protocol, right? It's not using iSCSI, it's not using Fibre Channel, it's using something really, really proprietary. But it's still a SAN, just like anything else. It is incredibly slow. It only works over 100 megabit per second connections. It is the most unreliable, most cumbersome, most non-scalable, useless, basic SAN device you could possibly make. It is literally worse than just a USB hard drive. But it's a full, unadulterated SAN. There is nothing about it that isn't a SAN. And I think everyone should own one and play with one to always really internalize what the word SAN means, because this device defines SAN with nothing to confuse you. Technically, a USB hard drive is a SAN device. If you plug it into a USB switch, ta-da! So what most SANs, the ones that people actually buy and use, do is really cool, actually. So if you're looking at someone like EMC VMAX, right, they make really cool SANs because their SANs have loads and loads of RAID, or if you get into like EMC Isilon, they're doing RAIN. But they have RAID layers and LVM layers and management features, and they have the full LVM with like the snapshots and stuff, and all kinds of high durability and monitoring, and really great stuff. And people start to associate that really great stuff, the magic sauce of the big vendors like EMC and HDS and HPE 3PAR and Nimble, right? Those guys are doing really, really cool stuff. But it's not because it's a SAN, it's because those vendors are putting a lot of magic sauce into those products. The last thing that I want to cover, and this is going to be very fast, is that, so we talked about protocols like SMB and NFS, and what happens when we take the file, not block, but the file appearance and put that out on a network. We talked about map drives, and we see this all the time. What we call that in a generic sense is a file server, right? We all know what this one is. I know I'm preaching to the choir. But a file server is simply the name of any device that intentionally serves this out onto a network. If we were to take that same product, a file server, it must be a file server, and then encapsulate that into an appliance physically, right? This is not a talk on appliancization, but if we were to appliancize any file server, we call that a NAS, and that is all that a NAS is a file server that has been turned into an appliance. This has become so common that it's starting to become a reverse naming convention, that people are starting to refer to file servers as NAS, which is not horrible, but it is technically not the same thing. It is whether one is general purpose or dedicated purpose, whether one is exposed under the hood or encapsulated under the hood. The actual what it does, though, is the same. The term NAS is meant to imply that you do not manage the system, you don't have full visibility into it. That's it. So very simple terms, but ones that are often misused and cause some confusion. And I believe that ends Storage 101. There were some things I wanted to get to. We didn't have time, but Val will just give us more to cover in a future thing. I think we covered what we needed to, and I think I have a minute or two for Q&A if anybody has anything. Or I was so thorough and complete that there isn't a question. Yeah?
I ran into another device, kind of like the SAN film, like MDAS. Same thing. Just a cheap thing that puts a single device on a network, uses its own special protocol.
And it presented as block at the end?
Yeah, I'm keeping a couple of them around.
Do you know who makes it?
I think the company might actually be called MDAS.
Okay, NDAS?
Yeah.
Okay, so what Travis was saying is that NDAS makes a similar device to the SC101 that is a completely useless block storage device just for the purpose of teaching you a lesson. That's really the best way to describe it. Let me tell you, you use an SC101, you'll be sorry, but you'll remember.
One of those MDAS things. You'll be sorry.
Yeah. Watson, did you have a question or comment?
Yeah. So when you're speccing out a SAN, what what is more important, CPU or RAM?
So the question is, when you're speccing out a SAN, what is more important, CPU or RAM? That's really going to be a question for your vendor. So if you're looking at a SAN as an appliance, or are you looking at building your own? Okay, so if you're looking at an appliance from a vendor, that's really going to be a question for them because every SAN is completely proprietary. So things that will be very influential in that are like if they're implementing RAID and it goes through the CPU, that may put a heavy or a light load on the CPU. It may, if you're having features that we didn't talk about, like dedupe, that could be a very large amount of CPU intensity. But if you're not using dedupe on the same machine, the amount of CPU that you need could vary wildly based on a couple, like I'm running RAID 6 versus RAID 10. I'm running dedupe versus not dedupe. Could easily be 100 times difference in CPU demands. And on this, in the same way, dedupe may make you require a ton of memory depending on the dedupe system that they're using. They may be using that as cache, and so you may want it depending on your workload, but your workload may be sequential versus random, and so those type of factors may affect you far more than just CPU versus RAM. And typically, a SAN vendor is not going to have you spec out those components, but sometimes. In which case you're kind of stuck with it. And then you have to know, the problem with that is if they make you spec it out, you have to know a lot about their under the hood implementation to know how those pieces will play into that specific system. So if you're dealing with, for example, an EMC vMax versus a NetApp, they're going to have totally different CPU and memory requirements and performance, and then your workload will vary and affect each differently. So no simple answer there. But your VAR should be able to do that for you as long as they have a really good understanding of your workload. That's kind of what they're there for. And I think we're wrapping up. I'm, of course, available if anyone wants to grab me for things. And thanks for coming out for Storage 101 and MangoCon 2016.